From ContainerDays Hamburg, this video is proudly presented by Dux IT.
So this talk is going to be about scanners as you know them, like Trivy and so on, what problems they have, why they have them, and what we can do about it. I work at a company called Sprint 1. Just a very brief advertisement block to make ourselves known. We are a contractor. Maybe many of you are also contractors. We provide IT teams, and then they develop software for other companies, usually enterprises, DHL, and so on. And we do the whole thing. So we start from the beginning, make UX designs, implement the thing, deploy the thing. That's what I do. And then we run it also. And instead of showing you a dry presentation full of facts, I want to try something different this time. I want to tell a story, and I hope that this makes the content stick better, make it more memorable. So every story needs a hero, right? And we have Tim. Tim is our protagonist. Tim is a typical DevOps engineer. That's what the HR department calls us nowadays. And he works as part of a team. There's a dev team, they make applications, and he then helps containerize that application, put it into a cloud, and he also puts all other kinds of software, third-party software, into the cloud, maybe databases, logging agents, reverse proxies, Grafana, I don't know, all that other stuff. So Tim is given a task by management to make the overall system more secure by keeping a close eye on all those components that they have deployed. So the problem is that if only a single one is vulnerable, an attacker could get into the system. And his job is to minimize this so that in the end you have this kind of situation. That's the simple management thinking. 0 CVEs equals safe, right? Well, anyway, it's a part of it. So Tim begins to research because he initially has no idea how to do it. And he also asks around, asks his friends, asks ChatGPT, does all that kind of research. And he finds quickly that there are nice tools to do that, right? You already know them probably, Trivy and Grype. So they should solve his problem and make it all measurable because, as I will see in a second, first of all, he needs to understand what these things do, and in very simple terms, you have a tool such as Trivy here. As an input, you give it a reference to a Docker image. Trivy then indexes it. It finds all those components in the image, and then it matches all these components against a proprietary database that is a compilation of all the other well-known databases like the NVD and the GitHub database and so on. And the output is a list of all those components that did have vulnerabilities. And the whole thing is great. It's like magic pixie dust. You just run one command and voila, you have your thing. Great. Because then Tim thinks, well, how do I solve this problem that I was given by management, the task? Well, they make it measurable. I can see how many vulnerabilities I have, and I just try to get them down to 0 over time. It will take time, of course. And I just need to apply that scanner to all the images that we have. And when I've done that, management will give me a nice bonus, and I'm happy, right? So on the implementation side, Tim thinks, well, it probably is good enough to have it on the one hand in my build pipeline, such as the Trivy tool running as a scanner job in my GitHub Actions pipeline or whatever I use. And on the other hand, use something like the Trivy Kubernetes operator to have this scanned continuously after the deployment. And that's all good and well. And he starts doing so, and he finds that for many kinds of images, there are many vulnerabilities, like 3,000. Like it's crazy how many. And now he updates all the components as good as he can, and he's not down to 0. He still has vulnerabilities. They come up and sometimes they go down back to 0, then they come up again. It's a constant struggle. What's going on, right? It's still a considerable number. So Tim asks researchers a little bit, and he finds out that these are called false positives. But he doesn't know yet what to make of this term. And then he also heard of the term false negatives, and actually there's a story behind it. He has a friend who works at a competitor, and let's call that competitor eCorp. And eCorp got hacked via open source components, even though they had Trivy, even though they already had done that, what he is still implementing. So apparently the Trivy scanner at eCorp didn't find the vulnerability that the hacker was able to find and exploit. So that's, Tim just realizes, I need to do more. I need to understand this whole problem space better. And so he begins to read up on the literature, and then he finds and dissects this false positive, false negative thing a little bit more thoroughly. So essentially, you have these two words that you need to combine. The second word, positive or negative, that's what the scanner thinks, what its algorithm, its heuristics determines, and what it reports to you. But then whether this thing is actually true is the first word. This is what an all-knowing being could determine, or what you could determine if you take the time and manually look into these things. So I want to fill now these 4 cells of the table and explain them in a little bit more detail. So first of all, we have true positives. What happened? You have a component that is known as vulnerable in the databases. The scanner finds it, and the scanner tells you, hey, it's vulnerable. And suppose that it is actually true that during the container's execution, this component is loaded to memory, its vulnerable code paths are executable, and an attacker could, therefore, execute them and exploit them. And you need to react, if you have such a finding, by patching the component, by removing it, whatever. The other case, however, is the scanner told you something is vulnerable, a false positive, but it turns out, for reasons as we will see in a second, there are many reasons, in this instance, this vulnerable component is not executable, or its vulnerable code paths cannot be executed. And this is a problem because whenever you get findings, these are, you just know it's somewhere here, but you don't know, is it here or is it here? So you have to manually look at those and determine which is which. And this is called also triage, and it can take a considerable amount of time. So now about the negative column. A true negative is a nothing to see here, move along situation. The scanner does not report something that does not need reporting. It does not report to you safe components. Why would it? It doesn't make sense. But however, the other last case, false negatives are a problem. There is really a vulnerable component in your image. The scanner misses it. It has like a blind spot and does not report something to you. So you think you are safe because the scanner tells you everything is good, but you are actually not safe after all. You don't even know it. So Tim thinks, okay, the false positives, they are annoying. We have to do triage, but the false negatives, they are really a problem. They're really dangerous. That's why the eCorp got hacked. Are we affected? How could we test this? And he has an idea. Let's investigate 8 of the top most downloaded Docker Hub images, of which Tim's company uses quite a few, just like a sample, and then look whether Trivy finds the vulnerabilities of the components. So you can do this by going on Docker Hub, clicking on open source, sort by pool count, and then you get lists like this. And the approach that Tim chooses is the following. For any given image, he does this. Let's suppose it's the Node.js image. He chooses a vulnerability, not 0 day, not super old, something in between, maybe a few months old. let's say this is this CVE 2025 something something. Then he determines some Node.js version that is actually affected by this vulnerability. Let's say this is 20.18.1. And he also researches which tags, plural, there are for this version, because often images have alternative builds for different Linux distro flavors under the hood, like Debian Bookworm or Alpine. And finally, he runs Trivy against these tags and checks whether Trivy finds the CVE, this 2025 thing, and also if Trivy even finds the component, which he can do by looking at the SBOM. And now I will let this sink in for a moment so that you understand the results. These are the top 8 images. Trivy does not find the CVE anywhere except here, but here it's an accident. What I tested was Python 3.12. What Trivy reported is, I found 3.11, and coincidentally, this CVE was also present in 3.11. Okay, fine, but that's like an accidental hit, kind of. So the other interesting part is, where did Trivy find the component? In most of the cases where it did not find the CVE, it was simply because it did not even find the component. So then how could it like make the lookup in the database? But there are some instances where it does find the component, but still the lookup in the database, for reasons I'll explain shortly, fails. So Tim thinks, like, what? How come nobody is raising this as a big issue? And he's like, he calls his friends, nah, you're wrong. No, but then they try it and they see, oh, fuck, he's right. And then they look it up, they look a little bit more closely and they find, oh, the scanner manufacturers, they know this. There are issues, they are like 5 years old. They don't fix it. You could also say, oh yeah, the scanner manufacturers, they have this in their manual, right? They explain it in detail to you. So the manual says, Trivy doesn't support third-party self-compiled packages and binaries, but official packages. Yeah, but the consequence is, many times, this means you don't find these components because they don't install them from the official repo. Why would they? The official repos often have very old software inside of the Linux distros. So now let's look at why do these false positives and why do these false negatives occur? Because Tim is like still, okay, he now knows the consequence, but why? Because only if he knows why, he maybe have an idea of how to fix it. So he looks at the code of the scanners, he looks at their manuals more closely, and this is what he learns. So back to the original image that I showed before, I just put it to the side. The first step, as I said before, is that Trivy indexes an image and creates an internal SBOM, an internal list of all the components. Yeah, but how? For this, there are kind of indexing algorithms, or you could call them catalogers, whatever you want to call them. I found 5 very common ones that most of these scanners use. The first one is metadata of the package manager of the Linux distro. So every image, let's say Postgres, is still based on some distro, in this case, let's say Debian. And this distro has some package manager, like apt, and this package manager stores the packages that it has been that were installed with it in a file like this one. And tools like Trivy can parse and understand these files. The second one of those 5 is for basically the same idea, but for programming languages, you know, like Python, Java, all these other programming languages, they have installers for the packages for you, Python pip, Java, I don't know, POM XML, and so on. So they can be parsed. Some tools like Trivy can also parse embedded SBOM files, like SPDX or JSON standardized formats that someone put as file into the image could also be parsed. You could parse the metadata of binaries. So there are programming languages like Rust or Go whose compilers can compile the information about what kind of software is this, what kind of dependencies does it have. It compiles them into the binary in a small segment. Also standardized format. Trivy can parse and read this information and get the data out of it. And finally, some scanners such as Grype, but not Trivy open source edition, have been aware of this problem that many people just copy binaries into the image and the scanner has no way of knowing what it is. And what they did is they maintain like a 1,000-line Go file with many, many regular expressions in it for file system paths where they know, where they really, some poor soul at Anchory, they typed in fluent bit detection, Postgres detection, Python detection, Perl detection. This fucking shit job what this person had to do just to detect these kinds of binaries in the images. Okay, so Tim understands that if anything goes wrong anywhere, like if there's a bug here, or if there's a bug here in the lookup, in the cross-referencing, of course there will be oversights, like these false negatives. So he begins to compile a list of false negatives, and he finds 5 very common false negatives. The first one is that a component was not installed via a package manager at all, but maybe as an example, it was just copied in. Maybe you have a Docker file, multi-stage. In the build stage, you compile the thing, maybe with C++, like not with Go, not with Rust, but something else, anything else, and then it you copy the binary in there, and the scanner has no chance. Second idea is you have installed the package via the package manager, but then you deleted the metadata of the package manager. Either you did this yourself, like actually put some run rm folder in your Docker file, or maybe you used a tool like Slim Toolkit, or it's called Mint, I think, today, who also thinks, oh, this file is not used at runtime, let's delete it. And then you have an image that the Trivy will always scan and say, you have 0 components, therefore you have 0 CVEs. Happy birthday. Third one, let's say the scanner detects a component. It was installed via the package manager, but not from the official repo of, let's say, Debian, but from somewhere else. So for example, if you look at Postgres, the official Postgres image, what they do is they build a Debian file, .deb, and then they install that Debian file. So it's a self-built thing installed via the package manager, but still not from the official repo, and therefore the cross-referencing algorithm fails because this package identifier and the version is no longer known in the concrete Debian database. Scanners like Trivy, they scope their cross-referencing algorithm to that distro that they usually expect packages to be installed from, because all those distros, they have their own vulnerability feeds. The scanner might also identify the component simply with a wrong ID or wrong version string than the ID it would expect from the database. So as an example, maybe some of you have known this Google DistroList project. They offer SBOMs. You can download the SBOMs from Google, and then you can type in Trivy, SBOM, and then you give it the Google SBOM, it will find 0. It will say, it's safe, no vulnerabilities, even if you take a 2-year-old SBOM, which of course must have vulnerabilities. This whole SBOM thing is, once you get down to the lowest level and all the leniencies that these SBOM files have, it's pretty bad, pretty crappy. Like implementation 1 being incompatible with implementation 2. And finally, simply the scanner, which uses its own database. Maybe there was just a temporary problem with the database. Maybe it is not up to date yet. Maybe Trivy had a problem building the database. Any kinds of things could happen why you miss a vulnerability. Okay, these were the false negatives. Now, what about the false positives? Why does the scanner sometimes annoy you with findings that are not real findings? So first of all, suppose the scanner, it could find a vulnerable component, but it's never loaded to memory at all. As an example, maybe you have a Postgres or other database server image, and maybe it includes even like helper programming languages, scripts, shells, whatever, but they are never active. And maybe the feature flags are also disabled by default, but it's still in the image for whatever reason, then this cannot be exploited if this binary will never be called, this Perl interpreter in this example. Or case number 2, I have 4 cases in total. The scanner finds the component because of the help of metadata, but the binaries that are actually potentially harmful, they have been deleted. That's like the opposite case of what I presented before. Somebody left the binaries in there but deleted the metadata. That could cause a false negative, and a false positive is if you do the opposite direction. So instead of doing apt-get remove of a component, which removes the files and the metadata, you'd maybe just made a removal of the path. Another example, this is one of my favorite examples, is there's a disagreement between what the vulnerability researchers think and what the software maintainer thinks. And since there's no court or no cage fight or anything that settles this, they say 2 things and they leave it like that forever. Easily identifiable by CVE numbers that are like stone old, 10, 20 years old. They remain because in this example, Debian says, oh, this is a feature, and the researchers say, no, it's a vulnerability, and it just stays that way forever and ever. And finally, many distros, they have, or most distros, they have security backports. As an example, let's say you have a version of curl where there's a CVE that says versions in a specific range are vulnerable. And let's say the scanner thinks it detected a version of curl that is within that range. So then the scanner would say, oh, it's vulnerable. But the scanner did not probably read the end. Because what you see here is versions are no longer major, minor, patch. They are major, minor, patch, dash, and then something, something, that each distro does a little bit differently. Alpine has this R0, R1, R2, and so on. Debian has this funky notation. Ubuntu is similar. And this just implies Debian has altered the version and security patched it for specific vulnerabilities. And if the scanner does not pick this up properly, then you get these kinds of problems. So often we try to think in terms of quick fixes. So Tim thinks, okay, I understand now, we have many problems. Can't I just do this and that and I will be safe? Just a small quick fix. And you could think that there are 2 solutions that work, but if you think more closely about it, maybe they don't. So one idea would be false negatives. Let's reduce them by simply running more scanners. So I'm having different kinds of scanners, reducing the blind spots. And even if this is true, it also increases the true positives because they all report different things to you, and then you just have more triage work. So you've traded one problem for another. Or you could wait for the scanner vendors, right? They will fix it eventually. They will never report false negatives and false positives. Yeah, you've seen the GitHub issues before, right? 5 years old GitHub issues. There's some reason for that. So Tim realizes, on average, scanners can, in certain cases, make mistakes. And you have to do some kind of manual work to get around this. However, what you also don't want to do probably is to determine the list of all your images, and then for every image you look into this problem deeply and analyze it, and you don't have the time for that. So my recommendation is prioritize. Think, like, get the list, skim over it, and identify those kinds of images that are really critical in terms of security, because user input, that could also be hacker input, flows through them. So I don't know, reverse proxies are very important, for instance. And then you have a condensed list of hopefully just a few images. And then for these images, I propose the following flow. The first idea would be research if you can replace the image. Because if you there's a new industry coming up more and more. They are minimal image distribution vendors, like ChainGuard, RapidFort, several others. What they do is they give you images that have much fewer components. So this solves the false positives problem, because the Postgres image, let's say, no longer has 200 something components, but maybe 30, 40. So it's like almost a 10-fold or 5-fold reduction. And therefore the chance is lower that there are false positives, but also the chance is lower that there are false negatives, because the image vendors have made sure to collaborate with the scanner vendors so that the scanners really find everything in these images. Okay, but suppose maybe you don't want to replace the image, maybe you want to keep using those that you already use, then you would have to manually look for false positives and negatives, basically like Tim did it for those 8 images that I showed before, using that workflow. And suppose you find false negatives, then again you have 2 choices. You could either go back to the root here and say, okay, we didn't want to replace it, but if it has so many false negatives, maybe let's replace it after all. Or alternatively, you would have to somehow cover these blind spots that the scanners have in some shape or form. In the worst case, you write your own extra tooling that is tailored to those specific images and runs their component names through osv.dev or any other open source APIs for CVE detection. But do you really want to go through all this engineering work? So that's the false negative part. Let's say you make an analysis, you also find false positives. There are a few very well-known workarounds for that. First of all, use of flags such as ignore unfixed. It will reduce greatly the number of findings for certain images. Also including those old disputes between researchers and image maintainers, all these CVEs that are 10 years old or older, they will disappear from that. You can also maintain ignore lists, because you manually found out it's a false positive, so you put it into some ignore list that the scanner understands. And finally, you could also talk to the image maintainers, asking them to maybe rebuild the image more frequently, to remove stuff from the image that is not strictly needed, and so on. So what about Tim? What did he do? Back to our story. Well, he went with the image replacement route. And now he can finally sleep better at night or at the beach, knowing that a tool like Trivy will no longer find false negatives, or will no longer have false negatives, and it finds few false positives. So to conclude, first of all, security is hard, and many of us are simply not security specialists. And there's so much stuff going on under the hood. So what I try to think of this problem on how to solve it is to outsource it. We are not security experts. We can do it ourselves, but we are not. It's not our core area of expertise. So we will do it somehow poorly, in a sense, probably, and still spend engineering hours. And I'm not sure if it's worth it. And the minimal image usage, this is outsourcing in the end. Of course, you need to be a little bit careful, because this is a new and emerging market. So more and more providers come up, and they will also be reduced again over time. So hopefully not always by Broadcom, but maybe, you never know. It's a at the end there will be consolidation, but still one effort is what you can't get around. Make your list of images and pick those by priority that you really want to look more deeply at, and that you want to replace with minimal images, or make sure that you are not having any blind spots. That's pretty much it. I have 2 more. If you want to take your cameras out, this is the time. I have 2 resources. The first one is a blog post. It's exactly what I just talked about. It's the whole material, but condensed as a blog post, so you don't need slides after all. The second one is a not yet published, but therefore password protected article that gives you a list of most of the free minimal images options that there are already on the market. So I made a very extensive research for all the programming languages, .NET, Java, Node.js, and so on, if you want to migrate to minimal images. Okay, that concludes my presentation. I'm curious if we have any questions.
So dash ignore and fist can also have false, negative, positive. What to do? Not trust at all?
No, of course. The ignore unfixed is only reducing the number of findings that it reports. And
Oh, sorry.
huh? Yeah.
You said.
Yeah, and you still need to go the route of checking whether it is correct. Well, like the ones that remain, for those you need to check, are they false positives or not? And if you don't feel like doing this, because the images has many, then replace it with a minimal image. Yeah.
Do you have better experiences with commercial scanners like Sneak or Sonotype IQ?
No, unfortunately not. I would have liked to try those, but neither our company nor our customers already had those. So I would have loved to also test, let's say, Trivy Enterprise Edition, because they also have apparently these regular expression matchings. But I would guess that it will still be imperfect.
A fun one. Did Tim get a bonus?
Yeah, he did. I hope this was apparent from the victory pose that he showed in the image.
Given that compatible SBOMs would help for internal images, please give hints to ensure Trivy works correctly with them.
This is tricky. I didn't find any implementation advice on embedding the SBOM, like creating your own SBOMs and putting them into the image such that Trivy really properly parses them and processes them. I tried this myself, and I actually then stepped through the debugger through Trivy, like who wants to do this, just to find out what kind of hierarchy of the SBOMs do they actually expect for it to match. This is a very difficult thing to do that I cannot give clear guidance on yet.
No worries. Last one, at least for now. How do you determine the true negatives? By manually checking the components in the image?
Yes, exactly. The blog post has a few more points or details about this. Essentially, you run Trivy, and then as an output, you give it an SBOM path. Then you open the SBOM in your favorite editor. Usually it's a freaking text editor. And you look at if it even finds the component in the right place. Because the wrong place is, it will always find the component, let's say Python, at the very beginning, starting with a package URL that starts with OCI://, but that's the image itself. That's not the right component. You want to find something like, I don't know, Postgres or Python server, client, these kinds of libraries. And if you don't even find them anymore, then you already see that the component is not detected. And as for the CVE, I mean, that's pretty easy to do, right? You research for CVE beforehand for a product, just with Google, and then check if Trivy finds exactly that CVE for your image.
Thanks a lot. We have 1 minute left. Do we have any question in the audience, perhaps? Oh, just bye. All right, let's move. So CVE has gotten a lot of slack lately. Any changes or replacement you see coming?
I'm not sure what is meant by that, CVE or CVSS.
I think it was CVSS.
Yeah, so CVSS, of course, has been ridiculed more and more because the score that they show is the worst possible scenario that could happen under any circumstances. But you are not in the any circumstances field. You have very specific circumstances. Maybe your software is not even exposed publicly to the internet and other things, and therefore you need more context. I know that already commercial security suites do this for you, so they combine. They can give you a kind of a questionnaire to answer to get your scenario, to understand your scenario, and then they also download exploitation in the wild scores such as EPSS, and they combine everything through some magic formula into a score that is more representative of the real danger lurking in this specific vulnerability for you, for your scenario. Yeah.
One last question. Can you use Trivy with an SBOM created outside of Trivy?
You can try, but that's what I said before. It will often fail.
Why?
Because the identifiers are not the exact same ones as Trivy expects, and also because Trivy reduces the cross-referencing to the distro that it detects the image in. So if you have an identifier, let's say a package URL that includes generic, where the lookup would naturally be the NVD, Trivy doesn't do that because it says, oh, there's too much false positive risk, and just tries to identify those from the CVE feeds from Debian or Ubuntu or whatever distro.
Okay, Marius, thanks a lot for this great talk. A big round of applause for our speaker, please.
Thank you.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.